Yeah, so today I wanted to speak about Jacobson rings, and then after that I want to return to associated prime decomposition and more precisely to symbolic powers, and so it will be more convenient to discuss special examples there. And now I want to make some kind of break and to speak about Jacobson rings. That's our motivation. So I will give the definition, and the motivation for this definition is that the rings where you have theorem of type of Hilbert-Milch-Stellensatz is satisfied. Yeah. So let me first give the definition, and then I shall explain the motivation. So Jacobson rings. So A is called Jacobson. If for any prime that lives in spectrum of A, yes, so that is a prime ideal. So P is can be written as an intersection of maximal ideals. So where, of course, you can, from the beginning, you can write this formula that M contains P. Yeah? So without loss of generality, this equation holds, then M of course should contain P, but you can form such formula, and in general you will have an inclusion. Yeah? So in general you have an inclusion that P is contained in this intersection, and if equality holds, then the ring is called Jacobson. Yeah, so what are different interpretations of these definitions? So let me write as the remark. So if you are thinking about, but by the way, why this is true? So this means that we have examples of non-Jacobson rings. So example of non-Jacobson ring. So the thing is that the main operation of commutative algebra just puts us out of this class of rings. So if you just take A as a ring with some ideal, so with some prime ideal, with A with a prime ideal, so you can localize it with respect to this prime ideal, and this is local ring. And for example, if it has no zero divisors, so when A does not have zero divisors, and if it is not a field, if A is not a field, so you have non-trivial ideals. Yeah, so except, yeah, so of course if you have P, then it is not a field. Yeah? But P could be zero from the beginning. Yeah? So if A is not a field, so you have so AP is a local ring, so P is only maximal ideal. So now after localization, so let me write it down maybe. So M is just PAP, and M is only maximal ideal. Because the localization kills all ideals that contains P, and so all other prime ideals should be contained inside P, and you have that 0 is prime ideal, but of course 0 is not equal to F. And so this means that after localization we just get out of this class. But notice that this is a localization with respect to infinitely, with respect to multiplicative system, which has infinitely many, well, in general case, it has infinitely many generators. So you cannot write down the element as a product of a finite number of elements. So this means that this if you can do such thing, you can actually take the product of these generators and generate multiplicative system by this product, and you get only a multiplicative system generated by one element, but the result of the localization will be the same. And this procedure is more complicated. So here the number of generators for multiplicative system, which is a complement to P, is infinite. And this operation gets out of this class. We shall see that the other operations, for example, localization with respect to one generator, a finite number of generators, cannot get out of this class. So notice that, so the remark, instead of taking any prime ideal, we can recall what is the main point in Hilbert-Nullstellensatz. So you can actually pick a radical ideal. Yeah, so if you take radical ideal, so that in this case radical, let us recall that radical is just the intersection of prime ideals containing I. And this applying this formula, so this implies that if A is Jacobson, then a radical of I will be written in terms of maximal, so it is P containing I, and you can use only maximal ideals in this case. So you can take only maximal ideals containing P that contain I. So and of course it is enough to take all the maximal ideals that contains I. So you can formulate equivalently that Jacobson rings are other rings where all radical ideals are intersection of maximal ideals. Why it is related with geometry? So because we were interested in the following setting, so Hilbert-Nullstellensatz says that if F vanish on the set of zeros of some ideal, so set of, so you have the case where A is a polynomial ring over algebraically closed field. Yeah, so we have a proof that at least. Yeah, so in this setting, yeah. So if you have that if the f vanish on v of I, then f belongs to a radical of I.
Честно, можно вопрос?
Да.
Почему у нас там пересечение по простым, оно стало по максимальным? Там же как бы не все максимальные
Не,
содержащие.
ну в смысле, если А Джакобсонова,
Нет, ну я понимаю, что...
тогда любой простой это пересечение максимального.
Да, но это содержащих этот простой. То есть как бы у нас
Да.
справа максимальные идеалы такие, что между
Но,
этим максимальным и есть некоторые
Ну
простые.
правильно, но как бы сам максимальный это можно взять в качестве промежутка.
Да, это правда.
Ну, это, ну, то есть это как бы то, что вы говорите, это не дополнительная сложность. Ну и просто мы вот этот P, да, меняем на P, по максимальному идеалу, что P содержится внутри M, ну и значит у нас просто тут стоят эти вот максимальные. Вот. Ну и как бы тут можно, so here in Hilbert non-Stilinsatz you can use this thing, or you can say that A can be considered, A can be a quotient. So we have proved that it holds for quotient of K T1, Tn. And so as the corollary, we have noticed that if f vanish on this set of zeros, then f belongs to the radical. But notice that so here there was a point where you can so if K is algebraically closed, yeah, so then the set of points, affine points, coordinate points of V of I that sits inside some affine space, yeah, so that corresponds to the number of variables. Then the set of coordinate points are in bijection with the maximal ideals containing I. So maximal ideals that contain I. So maximal ideals. So you may think of V of I as the set. Yes, so you can think of the functions that are vanishing on this set. Yeah, so you can take I of V of I. So it is the functions f such that f is equal to f of x is equal to 0 for any x inside V of I. Yeah. So you are looking at the functions and saying that functions are vanishing in the coordinate points. So this is coordinate point is equivalent to saying that Ix gives you the maximal ideal. So vanishing. So taking value of the function f of x is equal to taking f modulo m of x, and this is value in k, yeah, in the field k, since which is equal to the polynomial ring modulo this maximal ideal, yeah, which is actually x minus a1, etc., x minus an. And so you see that the vanishing is just saying that f belongs to So vanishing means that f belongs to this ideal corresponding to the maximal ideal corresponding to the point. So you can write down I of v of I as just the intersection of maximal ideals. Yeah, so the condition for the function is the following. So this is the set of functions f that such that f belongs to the maximal ideal for any x inside of v of I, and of course this is nothing as just intersection of this maximal ideals where x belongs to v of I. So this way, this ideal is just radical of I by Hilbert-Nullstellensatz says that Nullstellensatz says that this is just radical of I. And notice that here you have, when you're speaking, so why Jacobson rings are important and why it is important to give this notion as a separate thing. Yeah, so just because you see that we have made some kind of assumption. So this assumption was about algebraic closeness. But after that, we derive two things. So actually, we say that f vanishing on v of I, and we can reinterpret this thing, knowing that f is algebraically closed, this condition. And out of this, out of this vanishing, we can derive this thing. But you can change the condition of vanishing by saying that I is belongs to the intersection. So this is some kind of change this is some kind of changing more strict condition by a little bit a weaker condition, because a priori, yeah, so just out of this we are deriving that out of this condition we are deriving that f belongs to the radical, yeah, and we are interpreting this set as the intersection of maximal ideals, and these are actually two different operations. Yeah, so sometimes you need only knowing that I is just the intersection of maximal ideals. So idea is to forget about vanishing, to forget about correspondence about geometric points, well, coordinate points, and maximal ideals. And then so you change the notion of ring for the Jacobson rings, and what is the benefit? That more rings satisfies this condition. So benefit more ring satisfies this condition. Jacobson condition. And these are, for example, this is not clear, and this will be a subject of today's discussion. So if you take K so you get add variables to any field, this will be a Jacobson for anything. So is Jacobson not necessarily algebraically closed. And there, notice that here you have, when K is not algebraically closed, we have discussed also as a byproduct of Hilbert-Null-Stern ansatz that their maximal ideals, they correspond not to the points, not to the coordinate points, but sometimes they correspond to the Galois orbit of the point. Yes, so if you have Galois extension, or then you just have the Galois orbit, and the union of these points in the Galois orbits are precisely maximal ideals. So there we prove this kind of correspondence. And here the benefit is that sometimes you really don't need Hilbert-Null-Stern ansatz as it is formulated. So here you can actually you can forget about coordinate points and what is vanishing, and it is a way to say it. This condition for the ring is not passing to this kind of coordinate interpretation. And for example, when your algebra is not finitely generated over the field or over the other algebra, it is completely not clear what are coordinate points, but still you can ask about Jacobson condition. But yeah, so what we shall prove today, so theorem so suppose S is finitely generated algebra generated algebra over R. Where R is a Jacobson ring, then S is also a Jacobson ring. So, for example, all fields are Jacobson rings for trivial reasons. There is only zero ideal in the field, and as a byproduct, any polynomial algebra over the field will be Jacobson. And also, if n is maximal ideal, so this corresponds to the point. Then I claim, yeah, so in general, intersection of n and s is only n and r is only prime ideal. Yes, so the restriction. So this is operation of restriction or taking pre-image or intersection. So this operation usually makes out of so we know that it makes out of the prime ideals, it makes also prime ideals, but in general, if you take maximal ideals, it can happen that intersection is only prime ideals, and what this is precisely what we really used when we passed from a ring to a localization, yes, so that in some prime ideal. And this, so here this ideal is also maximal in R, so also maximal in R. And also you can take S over n, so it contains is finite field extension, finite dimensional field extension of R modular R intersection with n. So this is precisely what we have proved when we were proving Hilbert-Stellensatz, and then when, for example, when this field is when R modular M is algebraically closed, this tells you that S modular M is equal to this field. So this will be, so this is the generalization of the Hilbert-Stellensatz and what we actually were proving, but the proof is slightly different, and there are some interesting geometric observation that is not explicitly written in the books. I mean, the proof is written, and more or less I follow as in that book, but some geometric interpretation could be said there. So could be highlighted. So okay, so let me start with remarks. So remark. Yes, so you see that, so suppose you have S is Jacobson, and you have phi is a surjective morphism. And if you have a surjective morphism, yes, so that you have a kernel here. And if you want to, first of all, you can speak about maximal ideals if you have M is maximal ideal in R. Maximal ideal. Then you see that if you, well, in general, pre-image is not maximal, but if you are speaking about surjective morphism, so pre-image is also maximal. And also it is a preimage, of course, it is not equal to S. Yeah, so just, also proper maximal ideal. Proper means, sometimes when you use proper, you mean that it doesn't coincide with the whole ring, or with the whole set. So, then if you want to speak about prime ideals, you know that preimages will be also prime ideals. So if you have ideal in R, so some ideal in R, and suppose it is radical, so radical of prime, radical of I is equal to I. Then preimage is also radical. It's radical. And you can, so it is ideal in I, and since S was supposed to be Jacobson, it is intersection of maximal ideals M tilde that contain phi inverse of I. So this implies that I itself can be written as intersection of images of this maximal ideals. Yes, so that phi of M tilde, so where M tilde contains phi inverse of I, and this will be just the maximal ideals. So since you have this kind of bijection, it is simply the set of maximal ideals containing I. Also, yes, so you may think that I is prime, so if I is equal to P is prime, and so this is prime, then preimage phi inverse of P is also prime and contain kernel. For phi inverse here, it contains kernel, and recall that such maximal ideals. So this is characterization. Yeah, so that you have bijection between maximal ideals that are contained in R and preimages of these maximal ideals that contain kernel. Or so you may think that this I in bijection with maximal ideals M tilde that contain kernel phi. So M tilde in S is maximal, and it is bijection between ideals that contain kernel. So that's why if S is Jacobson, then its image is also Jacobson. So, and also, so if we think about this formula, yeah, you can derive that preimage of radical ideal is, of course, radical if you think about this property of preimage of prime is prime, and you can use either by direct definition of radical, or you may think that it is intersection of prime ideals that contain I, and you have bijection between prime ideals. It is, it is more or less equivalent, easy or difficult. It's more or less the same. Yeah, so then you have this kind of property, and then we shall need the following criterion of being Jacobson. So criterion of Jacobson property. So the following are equivalent. First condition that R is Jacobson. And the second condition is it could seem a little bit strange, but I mean it is important. Yeah, so for any prime ideal, so suppose so for any prime ideal P inside the R, the following holds. So if B is such element in R mod P, so such that localization with respect to this element is the field, so R B inverse is a field. Then R mod P is itself a field. Note that this holds for not for any B, but for special B. I mean, it is some kind of condition to make this thing a field. But this property, so we're deriving, if we know that this is a field, then R mod P is a field. Yeah. So note that R mod P is the main. So note that P is prime. Then R mod P has no zero divisors. Has no zero divisors. And this, of course, embeds R mod P. So R mod P embeds in this localization. In general, you cannot say that. So this is true. So also, So if so let me so this condition can be thought that it is a little bit strange, but let me explain why it has why it is natural. So geometric interpretation makes it natural. It is like in internet, any explosion makes the field better. Yes. So geometric interpretation makes this any stupid definition natural. So this is the following. So first of all, yeah. So what is just taking R mod P is almost nothing, so it is just saying that taking R mod P is passing to irreducible subvariety. Yeah, so you may think that everything sits in as some closed subset in AN. And then we are speaking about B. B is one generator, so it is could be thought of polynomials. And let us recall that. So you have B equal to 0. So let us recall that R mod P B inverse. Yes, it is the complement to this closed set. So complement, I mean, this is a set of functions, of regular functions on complement of the set of zeros, b equal to 0. And from our point of view, it is open set. And what we know about open set, well, what is our intuition in the Zariski topology? That you have many points here. Yeah? So many points. But what means that R mod P is a field? So R mod P is a field. So R mod P B inverse is a field. This means that complement to b equal to 0 consists of one point. Yeah? One point. But this implies that this would be a finite collection of points, but we start with irreducible variety. So this means that we started with 1 point. So we started with 1 point. So that means what we have started with, it is a field. Okay? So this means that R mod P is a field. Yeah, so let me start discussing this criterion. So let me prove the criterion, which is, I mean, it is not so easy. I mean, it is a little bit technical. So, okay, clear about this. So yeah. So let me start with proving this criterion. Yeah. So
А где вот мы в геометрической интерпретации пользовались тем, что у нас Джекобсона кольцо вообще?
Нигде, нет. Я, тут как бы... Нет, в смысле, что я сказал про геометрическую интуицию, что если бы мы говорили, что мы работаем в кольце полиномов, то тогда у нас были точки, и дополнение до замкнутого подмножества имело бы много точек. Но, правда, вот как бы заметьте, что why we were speaking about Jacobson property, we were thinking about geometric interpretation, where the field was considered variety in a finite space where the field was algebraically closed, and we said that the complement to the set of zeros of one equation is intuitively it is infinite number of points. But for example, if you take finite field, yeah, so what you can do? So on finite field, yeah, so even in a finite space, you have only finite number of solutions over your finite field. You have finite number of possibilities of putting coordinates. Yeah. So that means that if you take a subset, a variety of a finite field, at least a finite variety, then you will have finite number of points in this finite variety. And if you have a finite number of points, you can find the hypersurface passing through this set of points. You just take these ideals, take intersection, and you take an element of this ideal. So you can think of this directly. For example, you can take through each point, you can draw a hyperplane. Yeah, so that this union of hyperplanes will give you an equation. I mean, the product of these equations of hyperplanes, and the complement to the hypersurface will contain no points. So, of course, this contradicts this kind of statement, but this doesn't contradict. I mean, still, if you have finite field, then you can take the extension. So if so here at least Hilbert-Nullstellensatz doesn't work, and still you will have maximal ideals corresponding to the following situation, that reduction modulo this maximal ideal will be extension of your finite field. Finite extension of your finite field that is still finite field. So that means that if of course even if you have the hypersurface with those complement has no points, you can pass to the field extension such that the complement will have the points. Yeah? So this is some kind of explanation why still finite fields has this kind of Jacobson property. Yeah? So that you still will have many points because you can pass to the field extension. Yeah, so, okay, so let us prove, suppose that from 1 we will derive this criterion. This is easy. Yeah, so easy part. You will see it. But it's still one have to comment it, but it is easier part. Yeah, so suppose R is Jacobson, so your if you take R mod P, so it will be S. It is also Jacobson, as we have noted. And here you have note that S is domain. And 0 is a prime ideal. So this implies that 0 is a prime ideal because you do not have 0 divisors, and so that means you have this property that if AB is equal to 0, then one of them is equal to 0. And this implies that it is a prime ideal. So by Jacobson, yeah, so also in S you have some if so if S is already a field, there is nothing to prove. So if S is a field, there is nothing to prove. I mean, part 2 is evident, yeah, because for part 2, yeah, that will be out. If something is a field, then initial S will be the field. So you are taking, so 0 can be written as intersection of some maximal ideals. Yeah. So actually you can think by taking all ideals that are inside S. So 0 is intersection of maximal ideals inside X. Right. So now so now we know that 0 is not maximal. And we want to take take B, so inside S, and we can study its localization. So let us consider spectrum of this localization. Yeah, so we are interested about this thing. So our criterion says that if part 2, we have to derive that if we know that, so take B inside S, if in case S B inverse is a field, we have to prove that S is a field. But generally, so you can take spectrum, and spectrum will be what? It is the set of prime ideals Now you can just speak about bijection such that B is not inside P. So notice that this is equivalent to the formulation that so since S is a multiplicative set, when we are speaking about localization, we are taking multiplicative set. So we're taking multiplicative set BI and saying that any so intersection of this multiplicative set, let me write it not as ideal, sorry, so let me put it multiplicative set in the brackets. So any BI is not inside P is equivalent to say that if your BI is inside P and P is prime, so so this is equivalent to simply to say that B is not P. So since P is prime, BI inside P implies that B is inside P. Yeah, so of course claiming only B is not in P is a weaker condition, but not for prime ideals. For prime ideals it is equivalent. So so simply spectrum is just saying that you are taking prime ideals that are not inside P. But assume that S B inverse is a field. Then 0 is only prime ideal. That means that means all prime ideals of S are killed. So all prime ideals of S are killed by localization. Yeah? So meaning that all prime ideals satisfy this condition. So this means that B belongs to all prime ideals where P tilde is not equal to 0 and belongs to S. So P tilde is inside S. But notice that since S was Jacobson, so now we use this condition. So S is Jacobson. This implies that 0 is equal to the intersection of all maximal ideals. In particular, this so M can be thought that it is a maximal ideal, and of course it is not equal to 0. And this is of course this contain this is bigger than the intersection over all prime ideals P tilde, where so you can keep that P tilde is prime, and P tilde is not equal to 0, so it is non-zero ideal. But notice that if P tilde is not 0, so it contains B. So, but you see that B is contained here. Yeah. So since B belongs to any P tilde for P tilde is not equal to 0. Yeah, so by our assumption on the choice of P tilde. And this implies that B is equal to 0, of course. Yeah? So this is contradiction. And proves this in one direction. Okay? So, yeah. So let me prove the different in the different directions. So that so 2 implies 1. Yeah. So we need to establish that our ideal is so our ring is Jacobson. So we start with Q inside R. So this is prime ideal. So you have so we have the thing that satisfies our strange condition, but we have to prove that Q is equal to the intersection of maximal ideals where maximal ideals contain Q. So assume not that inclusion is strict. And what do we get? We get that there will be an element exists f that is inside the so of course so this inclusion so that q is contained in this intersection. So assume that you have an element of f that is inside of this intersection of maximal ideals containing q, and it lies in the complement to q. So what I claim? I claim that I want to find a prime ideal. So I wanted to actually get rid of this element of f. How we shall do it? So we shall find some prime ideal that after some moment will become maximal. So let me do it. So find P prime ideal so such that first of all P contains Q, and P doesn't contain F. Yeah. So P F is not inside P. So I claim that how to do it? So let us prove that such ideal exists. So proof of existence a prime and not maximal. So it will be prime, not maximal. So first of all, what you can do? So you can start actually with Q itself, yeah. So because and find maximal ideals with so find ideal P maximal with this property with property P contains Q and F is not inside P. So note that we already has when we proved the formula that null radical is equal to the intersection of prime ideals. Yeah, so we actually proved this thing. Yeah. So, but notice that how you can recall that how to prove it. So recall that you can take. So notice that you can pass. So you take R. Yeah. So you can pass to the code. So here we used actually that F is not nilpotent, yeah. But here we do not have this condition a priori, yeah. Но я просто хочу вспомнить, что на самом деле, ну как бы мы примерно вот это рассуждение уже делали, когда мы показали, что множество нипотентных элементов, ну как бы пересечение простых. Как мы это сделали? Ну, мы просто взяли не нипотентный элемент и предъявили простой, которого не содержит. То есть мы взяли максимальный идеал среди тех, которые не содержат вот этот элемент. Но тогда мы должны были знать, что этот элемент не патентный. Но давайте вспомним, что so recall that R mod Q is the domain, and F is non-trivial element. Yeah, so that means that I mean the reduction of F. So F in I is not equal to 0 in R mod Q. So you can it form the multiplicative, and it's even non-zero divisors. So you can form the multiplicative system. So take R mod Q and localize by F. So localize by F by its image, and so you can take maximal ideal there. So take M inside R mod Q of F is a maximal ideal. And of course, this maximal ideal, it won't contain F because F is a unit. So M that is inside R mod Q F. Yeah, so you take M is of course F is not inside M, since F is invertible. And take phi, the map from R to R mod Q F, and inclusion. So notice, take composition of R mod Q and inclusion in the localization. Notice that R mod Q was domain, so partial localization with respect to any multiplicative set is inclusion, and take P equal to this phi inverse of this is prime ideal since M is maximum. Prime since M is maximum. So you see that so we have constructed such ideal, and what is a benefit? So also it is specially related with element F. So note that if you take assume that assume that this ideal so the idea that we pass to now we pass to note that P is not P is not maximal in R, is not maximal in R since otherwise, so since we have the following condition, so since we have taken so Q was strictly contained in the intersection of maximal ideals that contain Q, and here we had an element F that was inside this intersection, but F is not inside Q. So if P is maximal, so if P is maximal, then P is inside this intersection. Yeah? So that means that P below is P satisfies the condition that P contains Q. So that so P is one of the ideals in the intersection, but F is not inside P by assumption. Yeah? So which is contradiction? Yeah, so because the existence of P in this intersection will get rid of the element of P. So of F. Yeah? So, but F is not in P, so this is contradiction. Yeah? So F is not inside this intersection. So P is not maximal, so we can take this R mod P, so we can pass to now to R mod P. And so let us put it R tilde, and we will get to the contradiction because for the following, so note that just what will happen if you apply the following. So notice that yeah, so now we can use the following. So we can say that if you add, now we can take R tilde and add F inverse. Yeah? Here. Yeah? So notice that you can think of sorry, here I wanted to pass to R mod Q. No, here I want to pass to R mod Q. So we passed to R mod Q, and here you have our ideal. And P tilde, so let us put pi to be the projection from R to R mod Q. And pi tilde is equal to the image of pi under this projection. Yeah, because pi was containing Q, the image will be, so this is prime ideal. So this is prime ideal in R mod Q. But notice that P R tilde, so if you look at it in the localization, so what can be said about this ideal? So notice that again that R tilde sits inside its localization because since R tilde is the main. So since R tilde is the main, it is the quotient by prime ideal. So, and this is precisely our maximal ideal. Yeah, so this is equal to, so the M, so this is maximal ideal. Because of the, so we have made the choice of P this way. Yeah? So this is maximal ideal. And this is non-trivial. but notice that notice that you can take the following. So if you pass to now, if you pass to R tilde just modular. So if you pass to this quotient, so notice, so let me just put it further. So notice that when you, so on one hand, it is just this localization modular maximal ideal. So from сейчас есть ладно, я просто секунду. So I wanted to write the following. So I wanted to take this thing and to say that you are factorizing it by maximal ideal. And since this is maximal ideal, so this is a field. So since this is, so we can draw it like this, that it is R tilde times F inverse modular this P R tilde F inverse, and we can put out localization, and so we can take this as R tilde modular P R tilde, and you may look at this localization. What we get? Yes, so this is a field. So this thing is a field, but in the same time, yes, so R tilde is Q mod Q. Yes, so just notice that R tilde modular P R tilde is just the following. So it is just image of P. Yeah. So let me just this is just R mod P tilde, R tilde mod P tilde, where P is the image, and this is nothing as R mod Q modular image of P. This is P mod Q. Yeah. And the second homomorphism theorem it implies that this is R mod P. Yeah. So you get the following. So we got the following, so that P was not maximal. So P was not maximal. Then R mod, but the choice of P implies that R mod P, when you add the F inverse. Yeah, so notice that in R mod P you can speak about F inverse because it is the mean. So this is equal to R tilde modular just modular P tilde where you added F inverse, and by previous this is a field. Yeah? So then by Jacobson property, by property 2, so we have assumed that the second part of criterion is true. This implies that So this is a field, so R mod P is a field. So this is contradiction. So this is contradiction. Okay, so as for criterion, we have proved that, so let me just make a break, 10 minutes break, and after the break we shall derive out of this criterion the main theorem.
Да. Вот это. Так, сейчас. Я не помню, как допустим, не падаю. Да, я тоже посмотрел на это. Давайте тогда Ну да.
Ну что, продолжим. Yeah, so you see that so this criterion holds, and now we shall derive the proof of the main theorem out of this criterion. So, see if page is finished. But by the way, there should be let me do some small remark here. So maybe it wasn't so evident. Yeah, so in when I have changed this, so there was adding f inverse here. Yeah? So I have written it as I have put this element out of the quotient. So let me comment on this. So slightly. So if you have more generally, if you have the sequence of modules, also remark. So if you have sequence of modules, so you can, S is a multiplicative set. I mean, this is just different. I use completely different notation. Then I can pick up a localization, so I can localize. And one sees that one proves that this sequence is still exact. This means that the localization of, in particular, this means that localization of so this embeds here, and the localization of M3 is just it is so if you take a quotient of M2 modulo M1 and localize, this is the same as taking M to S and localize. And we have used so this in the case where you have exact sequence 0.
Можно
Да.
S, я так понимаю, в М2 сидит или...
Что?
S где сидит? Да.
S это мультипликативное подмножество в А. Это
я
вообще M это модуля. Ага.
Ага.
And if you have the following situation that in the case that we have used, so we had the following situation that we have prime ideal R and R mod P, yeah? And we have S was a multiplicative set generated by F, and saying that we're adding F inverse is the same that is saying that we are localizing by S. Yes, so that you see that R mod P, if you localize by S, it is the same that R localized by S and P localized by S. So this is that was the equality that could seem to be a little bit not evident. I just want to comment on this. So, so now let us prove the theorem. Yeah, so what means that S is finitely generated algebra over R. This means that you have any S can be written as polynomial with coefficients in R and in the set of some variables. So that means that you have surjective map from, so this is surjective map. And we know if R, if we prove that, we know that if Rx1 is Jacobson, x1, xn is Jacobson. So this means that S is Jacobson, so this will imply that S is Jacobson. So it is sufficient to consider the case when S is obtained by adding one variable, so that it is sufficient to prove by induction on variables and the S is just Rx. So there is a special case where this Jacobson property is evident. So that special case
Сейчас можно вопрос?
Да.
Я правильно понимаю, что кольцо Джакобсона это то кольцо, где радикал Джакобсона совпадает с нерадикалом?
Это как следствие, да? То есть это для любого, то есть кольцо Джакобсона это такое кольцо, для которого радикал Джакобсона совпадает с нерадикалом для него и для всех его факторов. То есть как бы ну, можно переговорить. Ну, давайте это скажем. Ну, то есть как бы, so there was a question. So maybe it should be written on the first page. Yes, so that notice that. So I shall put it here that just somewhere. Давайте вот тут напишу. Yeah, so remark. Yeah, so notice that, so if you take A, so you notice that nil radical of A is just intersection over all prime over all prime ideals. Yeah? And since P is intersection of maximal ideals containing P, yeah, so this is equal to intersection of all maximal ideals. Yeah? Maximal. But notice that also if you take any ideal, so notice that nil radical of A mod I is just intersection of prime divisors where prime contains I modular I. Yeah? And this is equal to intersection of maximal ideals that contains I. Yeah? Mod I. And this is radical of Jacobson radical of A mod I. So if you know that that if this thing is equal to this thing, yeah, so and radical of I is just intersection of P inside I, and if you know that this is intersection of maximal ideals, M contains I, that you know that the Jacobson radical coincide with nil radical for any quotient. And of course, if you only say about A that nil radical is equal to Jacobson radical, this will be, of course, I mean, you cannot derive the Jacobson property because you can start with local ring. No, in local rings, no, you cannot start with a local ring. But anyway, this is a property for any quotient, not for the ring itself. So now this is more strong condition. Yeah, so notice that sufficient to prove induction on variables, so let me say something about the special case. So, special case when R is a field. And in this case, that this is Euclidean ring. And you see that zero, I mean that just prime divisors correspond to prime ideals, correspond to irreducible polynomials. So reducible polynomials over R over K, and of course the only thing that is non-trivial here is that I mean that 0 is also irreducible polynomial. Yeah, so that I mean you cannot say that 0 is a reducible polynomial. Yeah, so that's why you're speaking about reducible polynomials, and in this case the quotient is a field. In this case, ideal is maximal. So Jacobson property means that you can express 0 as intersection as some prime or at some maximal ideals. And you can use F and G coprime reducible polynomials. So that coprime irreducible polynomials. Yeah, for example, this G can be thought of divisors of F plus 1. Yes, so just G is a factor, irreducible factor. Of F plus 1. Yeah, so if F is irreducible, F plus 1 could be reducible, but then you divide by G. So you take its irreducible factor, and then they will become coprime. Yeah? So this is easy. And now let me pass to the following. So what we shall use? Yeah, so that suppose R is arbitrary. What we shall do? Then we have to check that. So to check that R of X is Jacobson. We have to do the following. So by criterion, we have to take ideal. So take P to be prime ideal in R of X. Prime ideal. So this is prime. So this is prime ideal. So put just S tilde equal to Rx modulo P. So this will be domain generated over so a domain generated over R. Yeah, so again you see that you have the so put S to be Rx mod P, and you have R of X that maps to so you have the natural projection from R of x to R of x mod p. And you have image of R. Yeah, so the pi of R is just R modular R intersection with P, so R tilde. So you take R tilde, it is the main generated over this is the main generated over R tilde by one element, by x. And suppose we have B is the element of S tilde such that adding B is a field, B inverse is a field. So this is sitting in fraction field of S tilde. So notice that it becomes the field, so it actually coincides also. Yeah, so also we notice that if you add an element and if it becomes a field, yeah, so that means that you can in particular invert the elements of F tilde. So also we have that knowing that adding to S something makes it a field also says that this field is just the full fraction field of S tilde. So so this thing becomes a field, so we have to prove that S is a field. S tilde is a field. So notice that there are two moments. Yeah, so you want to prove that adding an element is so you are using all the time the following thing. So you want to add an element and you are adding an element, but and you want to prove that R of x is Jacobson, yeah. But then you have to pass to the quotient, and here, so this thing will be again, so it will be generated by one element. So I mean, we are using all the time that the surjective map from a Jacobson ring is Jacobson. So the induction is, I would say, it is not done in a direct way. Yeah, so you are using this kind of operation. So you are not just using adding variables due to this kind of induction procedure. Yeah. So also we have the second statement. Yeah, it says that so we can move from S to S tilde to so we can move from S modular. So the second statement is related with maximal ideals. So we are moving from S to S mod n, and so this can be thought of some pi. Yeah. So I mean that I'm proving just I want to comment on the second statement of the theorem. The second statement of the theorem tells you that you are taking the maximal ideal in S, where S is finitely generated domain, and you are looking at the intersection of this maximal ideal and the ring R. And also you are thinking about this kind of situation. R maps to R mod n R. And here you have to, here this is a field. And what we have to prove that, so we have to prove, this is finitely generated. This is a field, this is M is only prime ideal. So it is a subset of the field, and S modulo n is finitely generated algebra. Algebra over R and R, and you have to you have to prove here that R is a field. Yes. So after the change of so we have to prove that R and R is a field. So we will be proving, so after the change of notation, we will be proving the following. So S is a field. So we are proving that R is a field, and S is a finite extension of R. Finite extension of R.
То есть теперь у нас S тильда это S?
Да, но S как раз нет. Вот там была S тильда, а тут еще S тильда не было.
А S это тогда что?
S, ну это исходная как бы алгебра, конечно порожденная на D.
Да.
И у нас было два утверждения, но первое, которое касалось джекобсоновости. Вот, джекобсоновость, ну, для джекобсоновости мы говорили следующее, что мы перешли к S тильда, которое было порождено одним элементом над R, да, мы должны были показать, что если так случается, что S b в минус первое поле, тогда мы должны показать, что S тильда поле, да? Вот, а теперь как бы тут то же самое, что у нас S, ну, порождено одной переменной, то есть во втором утверждении у нас S было порождено R от X было, да, порождено свободно одной переменной. Мы должны были показать, что, ну, тут даже не так, тут просто мы можем считать, что мы хотим просто показать, что если мы взяли максимальный идеал и пересекли его с R, то это тоже максимальный идеал и вот это конечное расширение. То есть мы хотим теперь показать, что если у нас была конечная порожденная алгебра над R, да, и если S поле, то R поле, и тогда и S конечно порождена над R. Это при условии, что R джекобсонова. Да? So, это как бы второе R, so R is Jacobson. So this is Jacobson. То есть это я как бы поменял, ну, то есть вот за сменой обозначений я поменял нам то, что мы должны доказать, да, то есть вот как бы в первом случае мы можем оставить, то есть как бы у нас всегда остается условие, что либо, ну вот тут это R тильда, оно Джакобсоново, и вот ну, здесь мы как бы берем S тильда, S тильда это область целостности, мы берем B, добавляем как бы обратный, это становится полем. То есть мы должны показать, что S тильда это поле. Ну давайте я напишу under assumptions. That R tilde is Jacobson, because it was a surjective ring from Jacobson R to R tilde. And S tilde is generated over R by one element. By one element. То есть вот такой переход нужно сделать. Хорошо? То есть как бы, ну вот заметим, что как бы, ну вот это, то есть по сути тут как бы два близких утверждения, да, что либо, ну что вот тут мы доказываем, что мы берем S тильда, уже это область целостности, мы добавляем элемент, и b в минус 1 получаем поле, если вот S тильда порождено одним элементом над Джакобсоновым кольцом R, то тогда и как бы мы должны просто показать, что S тильда поле. То есть не Джакобсоновость, а именно то, что это поле. А здесь мы как бы должны увидеть, что если S вы стартовали с поля, то тогда и R было полем, и S ну, уже было конечное порожденное расширение. Вот, ну, как бы, дайте я прокомментирую вот эту вот звездочку теперь. So let me comment on star, and then I will derive the first part. Yes, so just let me comment on star, improving star. And then derive the first part. About the skill. Yeah, so what about star? So now let me. So here you have the following situation. So you have R of t. So and it maps to S, so by phi. So that means that you are taking one generator, and here you have a kernel of phi. So what can happen here? So just this. So what we know about S. So here we know that this is the main. So from the beginning, yes. So now I have made the change of notation for S tilde. Yes. So just I put S tilde equal to S. Yes. So
вот сейчас у нас S стоит тильда.
Да. Теперь мы S уже заменили S tilde. То есть мы как бы я хотел прокомментировать как раз ну, вот как бы ту ситуацию, что тут происходит. То есть как бы вот это вот область целостности, но как бы so this is domain by assumption. On S. And the S is generated by one element. So this means that
А у нас
S
там разве array должно стоять и не array tilde?
Что?
Разве там array должно стоять и не array tilde?
Что говорите?
Ну, тут у нас array от t, а разве не должно быть array tilde от t?
Ну, да, давайте я как бы, ну, берем тильда, put s to be still, да. And, я не буду просто возвращаться к старым тильдам уже, поэтому я хочу, ну, уже их не писать, хорошо? Просто я буду писать те условия, которые мы написали для тильда. Я их просто буду писать для s. So S is generated by one element over R, and I assume that S is the main since S tilde was, I mean, in the beginning it was S modulo P prime ideal. So actually S tilde was R of X modulo P a prime ideal. So this is the main. So kernel, so since R is the main, since S is the main, this implies that kernel is prime ideal. Okay, this is prime ideal. Yeah. So claim that kernel is not equal to 0. Kernel is non-zero ideal. It could be 0, but it is not. So, and kernel is not 0 under assumption that да, извините, я тут как бы неправильно сказал вот про вот в том смысле, что смотрите, тут как бы тут как раз из сейчас. То есть ну, в общем, то есть, но как бы, но тут просто но тут мы как бы увидим на самом деле, то есть, so in the notice that in the course of the proof we shall see the following. So if S is obtained by adding one element, so notice that so suppose if S is not so the second part is so this part is more complicated than the first part, because under assumption so I wanted to emphasize that we shall prove together what we are going to prove. So here we shall prove that if you have B such that this is a field, so then we shall prove that S tilde is a field, and moreover we shall prove how S tilde is generated over R tilde. and that on the assumption that R is Jacobson, and we shall see that still they will be generated by one element actually, and it will be generated by one element with some relation. So there will be algebraic dependence on this. So I will during the proof I will say that we have proved star or we have proved one in the beginning. So we shall be proving this actually simultaneously, not one by one. So, but notice that we can make. So we are making both reductions to the case we are considering. So the claim that if you have the following, so on the assumption that there exists beta b in RT, so such that taking RT and adding B inverse as a field, so is a field, we shall be proving that kernel is non-zero. So actually, if S is equal to R of T and just notice the following. So in the first case, so note that for star, so let me do this remark. Yeah. So for star, R so S cannot be equal to R of T. Yeah. So S cannot. So the kernel can be not zero. So for star, kernel of phi is not equal to 0, since otherwise S is equal to R of T, and S was field, was assumed to be field. But if you take a ring, if you take the main and add a variable, it is always, I mean, this is just a polynomial ring, so if R is the main, so, but R is the main, and this is never a field. Yeah? So this is never a field. So this and non-trivial part is so kernel in the case of star is always non-trivial. So non-trivial part is to prove non-triviality of kernel in the case where you take R of T. It is you add B inverse and you get a field out of this. But notice that just prove that in this case, so kernel is trivial. Yeah, so when kernel is trivial, then S is equal to R of T. But you have added B, so R of T becomes a field. Yeah? So this is a field. But notice that here you have, so it is a field, so fraction field of R. Yeah, so sits inside this thing. Yeah. So this because it is a field, R sits there, so fraction field sits, and this implies that just this R of t, B inverse, is just so you can change. So put k to be a fraction field, so you can put it to be k of. So since fraction field is already here, so this can be viewed as taking k of t of B inverse. Yeah? So, but k of t is Jacobson. Is Jacobson. So this implies that k of t is a field because so by criteria, yes, so that it is Jacobson. So adding a variable, so so since this is a field, so since this is a field. This implies that k of t is a field. Yeah? So this is contradiction. So this this arrow, I mean this arrow is by criterion. So by criterion of being Jacobson. То есть вот мы как бы предположили следующее, что мы предположили, что вот ядро не нулевое, вот это поле, да, то есть мы свободно присоединили переменную, но не к области целостности, а к R. Но за счет того, что когда мы присоединяем переменную, у нас получилось поле, то в этом поле и КТ лежит, да? Но у нас по индукции, ну, по предположению, да, первый шаг, КТ это Джакобсоново кольцо. А значит, как бы из того, что КТ поле, следует, что КТ тоже поле. Да? I have written, so this is a field by a criterion of being Jacobson, so this is contradiction.
Честно, можно спросить, а где
Да.
вы использовали конкретно то, что S это в точности ART?
Ну, как бы только в том, что когда вы к РТ прибавляете b в минус 1, то вы получаете, что это все равно, что к т прибавить b в минус 1. Ну, и что вы, что как бы, ну, в смысле, что просто так бы что произошло? Так бы у вас было алгебраическое соотношение на КТ, правильно? Это дало бы алгебраическое соотношение, ну, R от T по КТ, и оно бы дало алгебраическое соотношение в КТ. Но когда мы КТ факторизуем по алгебраическому соотношению, то тогда вы получаете просто поле, да? КТ по неприводимому многочлену это поле. Поэтому, ну, как бы ничего плохого мы вот тут бы не получили. То есть, как бы мы получаем, что все это, ну, как бы внутри, то есть мы взяли КТ, прибавили элемент, и вот оказалось, что это поле, ну, значит, КТ поле. Если бы КТ просто еще факторизовалось бы почему-нибудь, то тогда бы оно могло быть полем. Что и сейчас произойдет? So now just yeah. So and now we shall do the following. So yeah, so now we have to work with kernel. Yeah, so now I want to embed kernel in yeah, so now I want to embed kernel in the fraction field. Yeah, so that here you have natural inclusion into the K, which is fraction field of R. And here you have S tensor K over R. And so here you have also inclusion. And here you have kernel tilde. Kernel phi tilde, and since you have inclusions here, yeah, so this kernel is just a kernel of phi tilde is obtained by intersection of kernel of phi, just intersection of kernel of phi tilde, intersection with RT. And notice that K of t is a Euclidean ring, so K of t is Euclidean. So this implies that this implies that kernel of phi is generated by one polynomial. Yeah? So it is generated by f, the reducible polynomial. Yeah, so it is generated by polynomial, but already yeah, so notice that yeah, so that if notice that S, so if you take S tensor K, yeah, so notice that S embeds into S where you added B inverse, and this is a field. So this about this thing, you may just think that you inside. So you may think that this sits in the fraction fields of full fraction fields of S, but yes, where you add B inverse. So since you have this inclusion, then this is also so this thing, and so since this is already a field, and this contains image of R, yeah, so this means that S tensor K R is a subset of S B inverse. So this is domain. So this is also domain. And this implies that this S tensor K modular R is domain. So this means that kernel of phi tilde is primary, so is prime. And this means that you have kernel of phi is a reducible polynomial. Yeah. So generated by a reducible polynomial. Now we shall analyze. The problem is that this irreducible polynomial. It is not. You do not have a priori knowledge about its coefficients. So you cannot say. So in terms of KFT, so thinking of. So this polynomial cannot have, so it's not clear that it have integer coefficients. So but you are working over k. So you can multiply here. So at least as this ideal, you can make this to this polynomial can be supplied integer coefficients, but it is not integer polynomial. So let me write this down. So this means that now f is generated by the kernel. So the kernel is generated by one polynomial, and get rid of denominators of f. F, and so you get that the polynomial f of t is equal to an tn plus etc. plus a0. Yeah. So where ai are elements of R. And now we want to make the extension integer. So aim to make integer extensions of R. Yeah? So in order to make the extensions integer, so you have to get rid of these coefficients. But how you can do it? You can divide by it. Yes, so you can consider xn plus a plus. You can just divide by this coefficient. X. Notice that So notice that x is generator of S over R. Yeah. So what is the problem? For the field, so you already see that now kernel is a reducible polynomial, it is non-trivial. So you see that fraction field of S is finitely generated over fraction field of R. Yeah, so that fraction field of S is a finite extension of fraction field of R by this precisely this generator X, and because it satisfies this minimal polynomial. Yeah, so X f of X is equal to 0. So you see that but if you divide by an, yeah, so you see that this is integer polynomial. So this implies that S is integer over R where you add an. Yeah? But we are interested in applying lemma about integer extensions. And you know that S beta is beta inverse is a field. Yeah? So you know that this is a field. Yeah. So we know from the beginning. So we have to use this information somehow. Yeah. But B inverse is now element of so via belongs to S, which sits inside S of AN inverse, so this is integer over this one. Yeah, so S of AN, so if you add inverse, it will be integer over this thing. So you see that B is integer over R of AN inverse. So this means that B satisfies integer polynomial Q of t over R with denominator, and also assume, so by clearing denominators, clear denominators, so let me take it Q tilde, so clear denominators over R of Qt over R to obtain some Qt Qm of Tm plus etc plus Q0. And so this is an equation for B. So Q of B is equal to 0. And we have to write down an equation for B inverse. And notice that B inverse satisfies equation ну, какому уравнению b в минус 1? Ну, просто вы от Q вы ставите t в минус 1, но это, конечно, не полином, вы его должны умножить на какую-то степень, на степень, ну вот его степень. So you have to B inverse satisfies Q of t inverse. Of course, it is not polynomial over t, but you can multiply by tm to get a polynomial. But it will have highest coefficient q0, so you have to divide it by q0. So then you see that this is integer equation over R where you add the denominator Q0. So this implies that SB inverse is an integer if you add the so SB will be a integer if you add the denominators for so this will be integer over R where you add this Q inverse, so Q0 inverse, just because you have this integer equations where Qi are elements of R. So what does it mean for us? So let us recall lemma. So recall lemma that if B contains A and B without zero divisors, and B is integer over A, then B is a field if and only if A is a field. So B. А? Ну я и говорю, recall the null. как бы, вспомним лемму. Я ее просто сформулировал, я не буду доказывать, не волнуйтесь. Я это тоже помню. Yeah, so recall this lemma. So this implies that if S beta inverse is a field, and it is integer over R mod Q, so this implies that R Q0 is a field. But notice that R was domain. So so this is a field. But notice that R is domain. So note that by assumption R is domain and the R is Jacobson, so this implies, and this is a field, so R is Q0 inverse is a field. We know that it is a field. So this implies that R is a field by criterion. By criterion. But then you see that already. Yeah, so just already you have S. S is generated by R of X. And you see that S, if you add S to S, if you add an inverse, so S is integer over R. So S is integer over R where you add the denominators an, but R is already a field, so this is equal to R. So this means that this means that again by lemma, so by lemma S is a field. S is a field. То есть вот такой вот трюк. Вот. То есть как бы, мы все время как бы пользовались тем, что мы работаем внутри областей целостности, поэтому как бы, но вот мы хотим показать, что вдруг мы добавили элемент, мы получили поле, и это было сделано следующим образом. Мы получили с одной стороны, что сначала мы получили, что S, трюк в том, что мы можем тут разрешать как раз знаменатели у R. И за счет того, что мы разрешаем знаменатели у R, у нас получается целое расширение. Но как бы тут, лемма вот о целых расширениях, она сильная, то есть в результате у вас должно быть поле. Но вот как бы из-за того, что вы взяли S, присоединили целый элемент, у вас получилось первый раз целое расширение, потом вы, оказывается, можете добавление элемента, теперь B становится целым над вот этой штукой, над R с добавленным элементом. За счет этого вы можете обратить, получается, то есть обратный B тоже он может быть сделан целым, но если вы допускаете знаменатели над UR, а в результате у вас получается поле. То есть трюк в том, что теперь вот это вот S-бета цело над чем-то, где что-то добавлено к R, то есть вот это поле, значит R от Q тоже поле, вот, но R от Q в минус первый, но как бы дальше вы видите, что как раз к R что-то добавлено, А R Джекобсонова, это вот как раз тоже основное место, где используется джекобсоновость. Поскольку вы взяли к что-то добавили, получили поле, используя, что R Джекобсонова, вы увидели, что на самом деле, что R уже поле, а дальше вы видите, что S у нас цело над R, к чему добавлены еще какие-то знаменатели, но чтобы говорить уже, но S тогда не становится как бы, то есть S цело получается над вот этими элементами, но вот эти элементы, они совпадают с R. Как бы значит и S уже исходно поле. То это нам и нужно было для доказательства джекобсоновости. И мы видим заодно, что тут как бы, если вы стартовали с поля и ничего не добавляли, то как бы это тоже можно провести рассуждение. Тогда вы видите, что тогда это рассуждение становится короче, да, просто потому что вы здесь добавляете тогда что происходит? Тогда у вас S S уже поле, вы видите, что S получается добавлением к RAN, то есть как бы, если вы хотите звездочку доказать, то мы что должны сказать? S это поле, мы должны доказать, что R это поле. Но если вы S получается добавлением одного алгебраического элемента, можно добавить знаменатели, тогда S становится цело над R с добавленными n в минус первыми. Поскольку S поле, то и вот это поле, но поскольку вот это джекобсоново кольцо, то мы можем стереть знаменатель и как бы получить то же самое. То есть тут как бы, формально говоря, тут применение к разным R и A, давайте я это тоже, наверное, запишу, что, формально, чтобы это было, и закончим. То есть, давайте напишу, что proof of start. So, if S is integer over R of an inverse, S is a field, so that means that R an is a field, so R is Jacobson. So this implies that R is also a field, and this implies that S is a finite extension of field. Because already it was one element. Все, тут как бы уже нам пора заканчивать, но как бы там, соответственно, как бы вот такая теорема. В следующий раз я хочу поговорить о артиновых кольцах, символических степенях, и вот отсюда я выведу уже теорему о Круле, о главном идеале. А во время этого нам понадобится понимание как раз ассоциированного примарного разложения. Особенно это полезно, потому что мы будем видеть, почему как бы символические, нужно вводить символические степени, и чем они лучше обычно. Это видно только, наверное, с помощью ассоциированного примарного разложения. Спасибо.
Спасибо.